All right, so on Friday we gave a brief review of basic tree data structures. We got through as much as we could with the limited time that we had. We modeled the problem. We created several Python classes. We did some basic search, insert, and we didn't get to do the entire thing of delete. But I was using that as, and of course there's pre-order, in-order, post-order, and BFS. I use that just to remind ourselves of what trees look like. What I want to do today is actually do present an application of binary trees. Now, these are not binary search trees. This is just using binary trees to solve a different problem related to compression. So for that, we're going to be looking at Huffman Coding. Remember, we are online, so if you have any questions, you can go ahead and go to the live stream here. But Huffman Coding, first of all, we need a little bit of foundations here. There are two parts to coding theory. So coding theory is a branch of mathematics, a branch of computer science, engineering, however you want to look at it. The first branch basically is to add redundancy to ensure information is not lost over a noisy channel, And what we mean by a noisy channel could mean many things. It could be transmitted over a network, a wireless network, where some of the bits get garbled because of interference. It could mean that we store this on, like, say, a CD or a DVD, and that's a noisy medium because you can actually scratch it up, right? And you can lose bits, you can lose information. So what we want to do is we want to add redundancy to the information so that we can recover, we can either detect those errors or that we can recover from those errors. Now that's the branch that we're not going to look at. That used to, at least at one point, that used to be an entire upper level graduate course where you go through all the various schemes of linear LDPC codes, a bunch of codes that are actually used in practice. We're not going to do that. Instead, we're going to look at the other branch of coding theory, compression, right? Where you want to either remove redundant information or reduce the information or reduce its size in order to make it smaller, right? So for example, the classic examples of this would be like your typical zip file, right? If somebody says zip that up and send it to me, right? Then that means that you're taking all this information, you are making it smaller so that you can transmit it over email and actually, be within that 10 megabyte limit or whatever that Gmail imposes on you, right? Or it could mean that you are actually cutting out redundant information. For example, the lossy compression. For example, MP3s, right? MP4s, right? What else is there? JPEGs. PNGs, etc. Right? All of those are compression algorithms that cut out additional information. For example, with video, right? If you're fading in from black, right? You've got 1 second of black. That's 60 frames of nothingness, right? So you don't encode every single pixel in the entire frame for times 60. Instead, what you generally do is you encode differences. If the background, for example, is the same, you don't encode that over and over again. Instead, you cut that information out and you only say, all right, well, at some point, this pixel changes or these collections of pixels changes. And you can actually see the artifacts of when that screws up, right? That sometimes things will go green but you can still see the shape of the person moving around, right? That's because it screwed up from the last keyframe, and it screwed up the original encoding of the colors, but the changes were actually encoded correctly, right? Or you JPEGs, right? You can make them really, really small, but then what happens? They become very, very pixelated. You are losing information by approximating these things. The other version would be lossless compression, which would include your zip files or your gzip files, or in this case, Huffman Coding. We do not want to lose any information here at all. With an image, it's not that big of a deal if it's a little bit more grainy, right? The human eye maybe not even can see the difference between it. But with other information like text-based information, imagine if if you cut out all of the vowels or something, right? It would kind of make it unreadable. Or if you garbled the information, then you don't want to lose information in certain applications. And that's where lossless compression comes in. Yeah, go ahead.
Do you know if like there's a certain frame rate you get to where the human eye cannot detect any difference?
I think it's 60, isn't it? Gamers out there, tell me. 44 hertz around, yeah, any more refresh rate than that. And
there's people who use 360.
my eyes are better than every human's eyes, every other human's eyes, right? 60 frames per second, though, I think is pretty standard. Anything more is just, you're not going to notice, are you?
You can tell.
Oh, you can?
Yeah, like if you use a 144 hertz monitor, you notice especially like the cursor is a lot smoother. You don't notice it like
Okay.
around so much.
I always assumed it would be like those TVs that have that stupid mode where it kind of it just looks weird. I don't know what it's called, but
It's something that if you never try it, you never know. But once you like use a monitor with higher refresh rate, you can like tell the difference. And
you can never go back.
that's basically how it is.
Okay, 1,000 frame, like 1,000 frame rates per minute on Minecraft is gonna make a difference. I don't know.
Never try it at higher refresh rate. You'll never have to buy them every time.
Okay, I'll believe you. Anyway, the application that we're searching, that we're going to be looking at today is Huffman Coding, where you don't want to lose any information, so it's a lossless compression algorithm. But it basically is going to take advantage of the fact that English or natural language is highly structured, right? English, in fact, most languages, natural languages, have a lot of redundancy, right? It's non-uniform, uniform distribution of letters, right? For example, common letters, right? Yeah, E, R-S-T-L-E, R-S-T-L-E, right? Those are the ones that you're given for free in Wheel of Fortune or whatever now, right? And less common letters such as Z and Q, right? The idea here is these shouldn't be created equally, right? The idea is that if you use a fixed length encoding, right? For example, ASCII text, right? Where everything, all letters are 8 bits. Technically, there's 7 bits in the actual ASCII text table, but we'll just go ahead and say that they're 8 bits, right? For a fixed length encoding, it treats everything equally, like that they're all equal. They're all equally likely to be seen in an actual text file. Instead, what we're going to do is we're going to create a variable length encoding. That is, more common letters will get shorter code words, shorter encodings, while rarer letters, will get longer code words. And the idea here is that if we can compress the number of bits required for common letters and pay for that by extending making uncommon letters even longer, or even cutting out letters that aren't used. For example, for a particular text file, if there is no instance of the letter Q, we can go ahead and throw that out entirely. We don't even have to encode that. And the idea here is that you can potentially get the compression down so that you have 50, 60% of what it originally was, right? So for example, but there are some problems here that we have to take care of, right? So problems. With a fixed length encoding, all decodings are unambiguous. Unambiguous, right? That's because everything is expected to be 8 bits, 8 bits, 8 bits. We know exactly where one character starts and the next character begins, right? We know where it begins and ends because it's 8 bits, 8 bits, 8 bits. That's block length encoding, right? Block length encoding. But if we go with a variable length encoding, can be ambiguous. Right? So for example, where is my example here? Let's see. Let me go ahead and give you, I don't know, A, B, C, D. Suppose that we encode these with a variable length encoding of 0, 0, 1, 1, 0, 1, 0, 1, 0, right? So A gets encoded as a 0, B gets encoded as 0, 1, 1, 0, and 0, 1, 0, right? And do I have an example of, yeah, let's just go ahead and go with this. Suppose that the message, I'll just keep it really, really simple here. Suppose that we transmit a message and at the other end we receive this, 0, 1, 0. What was the original message? It could be decoded as D. Why? Because D gets encoded as 0, 1, 0. Is that the only thing that could have been transmitted? What else could have been transmitted? B, A, right? Why? Well, because it would be B, which is 0, 1, and then concatenated with a 0, right? So which one is it? Who knows, right? Without some additional redundant information built in, we don't know, like a delimiter. We could say, okay, well, we'll put in a delimiter here, a comma. But guess what? Now that comma needs to have an encoding because we can only send zeros and ones. Right? To solve this, what we can do is create what's called a prefix-free encoding. Right? So solution is to create a prefix-free encoding scheme. Right? No code word, no encoding, appears as the prefix of another. So my first observation here is that with a fixed length encoding, you automatically have a prefix-free code. Right? Why? Because again, everything is a block. 8, 8, 8, 8, 8. If 8 bits were the prefix of another code word, that they would be the same code word. The same 8 bits here, the same 8 bits there. This is not prefix-free. Why? Because A appears as the prefix of B. B appears as the prefix of D, etc., etc. So here, let's go ahead and create a new encoding here that is prefix-free. What if I did instead A, B, C, and D? What if I did 1, 0, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 0? Now, is any of these code words the prefix of another? 1, 0, nope, nope, nope. We're good to go on that. What about 0, 1, 0? Well, it can't be the prefix of something that's shorter, so we're good there. It's always going to be the prefix of itself, so the technicality here is that any other code word. It cannot be the prefix of C because they have the same length. B is not the prefix of D because it's 0, 1, 1 there. 0, 1, 1 is not the same as 0, 1, 0. Likewise, this one's not the prefix of this one, and this one can't be the prefix of any of the other ones. So here, it's completely unambiguous. It is not, a delimiter like a comma is not necessary at all. So my goal here is twofold. I want to make sure that I've got a variable length encoding that is completely unambiguous. In other words, it's prefix-free. And I want to follow this general guideline that for uncommon letters, we will assign shorter code words because they're going to appear with a higher frequency. For less common ones, we're going to have a longer code word because they don't appear that often. So we can afford to go ahead and blow up the size of the code word without having, overall the entire thing will be, hopefully, if it's correct, will be compressed. Okay. So here's the idea. The idea that I'm going to pursue with Huffman Coding is I'm going to build a tree. Build a tree greedily. Right? Greedily. Right? What I'm going to do is I'm going to first compute the frequency or count of all characters in a file. Right? So that I know which one is the most common, which one is the least common. If something doesn't appear in the file, it's not even part of the input. I throw it out immediately. If I've got a file with no Z's in it, just ignore the Z, right? And then what I'm going to do is progressively, or I'm going to associate each letter or character with a tree node. In this case, it's going to be a leaf. Eventually, a leaf in a binary tree. Not a binary search tree, but a binary tree, along with its frequency. All right? Then I'm going to combine iteratively, combine trees by combining the least weighted trees until you have formed a single tree. Right? When you combine, the weight of the new tree is equal to the sum of its left-right child's weight. Okay? Now there's the general outline. Don't worry about the details because we'll fill in the details as we go along here. Let's take a look at an actual example. Here is a potential input to Huffman Coding, where I've got 1, 2, 3, 4, 5, 6, 7 letters. Right, this is just a toy example. Of course, if you had actual English letters, of course you would have the space, right? You would have punctuation. You would have all the letters, both uppercase and lowercase. I'm just going to go ahead and go with this as a simple example. Right? Now here's the first phase. What I'm going to do is I'm going to associate each one of these characters with one of the nodes over here, and I'm going to associate that frequency with it as well. So in other words, A is going to be associated with a frequency of 10. That means that A appears 10% of the time. That if I were to randomly extract a character from the file, with 10% probability it'll be an A. Right? B will be 0.15. C will be 0.34. D, E, F, and G. There we go. With 0.05, 0.12, 0.21, and 0.03. You'll note here that all of these frequencies sum to what? 1. Why? Because you have a 100% chance that it's one of these things. Okay? So how would you go about doing this? You would go through a file, count up the number of times an A appears, count up the number of times a B appears, etc., etc. Divide that if you want to, or just keep the character counts themselves. Yeah,
That's just linear.
that's linear through the with respect to the size of the file. Yep. All right. Now, what I'm going to do is I'm going to start, that's the initialization in it. Now what I'm going to do is I'm going to iteratively combine trees, right, by combining the two least weighted trees. Right? So in this particular case, which ones are the least weighted, where this frequency is our weights? D and G. You'll note here, how many trees do I have over here? I actually do have trees. They're trees of size 1, right? So I have 7 trees here. Right? You can have a node, just a root element, right? Just like we started out with our binary search trees. When you insert one element, you have a tree still, it's just that it's one element. So what I'm going to do is I'm going to start combining these things. I'm going to take G over here, and I'm going to take D. Oops. Undo. I only want U, D. And I'm going to combine them into one new tree. Right. That new tree will have a new weight, which is the sum of its two subtrees. In this case, it's 0.08. There we go. And now I take this tree and throw it back into the mix over here. And I won't do that because I'll end up not being able to move anything anymore. Right? How many trees am I left with now? 1, 2, 3, for 5 of the single node trees. Somebody suggested that we call those seeds, right? Because they're a single node, right? You plant the seed, right? And then we've got this tree over here, which consists of 3 nodes, right? There are 3 nodes in this tree because you've got 2 children here, 2 leaves, and 1 internal node here. So when I started out with 7 trees, now I'm down to 1 by combining 2. Eventually, I'm going to get down to 5 trees. 4, 3, 2, 1. When do I stop? When I've got 1 tree. Okay? So what's the next step in the algorithm? I've got these 5 trees over here and this 6th tree over here. I combine the 2 least weighted trees. What are the 2 least weighted trees now? Yeah, this thing, right? And what? A. All right. I'll combine them. Let's see, I put the largest one on the left. It really doesn't matter. Although when you program them, you'll probably want to be consistent about it. And there's the left child and there's the right child. The new weight of this one is 0.18. Okay? And I didn't take the decimal point with it. Weird. I am now down to how many trees? 5 trees. So which ones do I combine next? The 2 least weighted trees are going to be B and E. Right? Why? Because the weight of this tree is now 0.18. Okay. So take this one and combine them into a new tree whose sum of the weights is 0.27. There we go. There. Now I've got 1, 2, 3, 4 trees left. Yeah, go ahead.
So when you program this, does node hold tuples in some cases then?
Node, well, that's a good question. How would you program your node to hold? What would you need to hold? You would need to hold the character. If it's a leaf, the character and the frequency. If it's an internal node, the frequency or the weight, whichever one you want to call that. You could hold a letter that is none, right? And then that's how you know it's an internal node as well. Only the leaves are going to hold the additional data. Okay. What do I combine next? Now I'm down to 4, right? The weights are 0.34, 21, 27, and 18. So I will combine, move this one over, give myself a little bit more room. I'll combine these 2, right? Into a new node tree that is 0.39. There we go. On the next iteration, what do I combine? Now I'm down to 3. I combine this one and that one. And I've got 561.61. There we go. I'll move this down because on the last iteration here, what am I going to do? I'm going to combine the 2 remaining trees to get 1.0. All right? Now that's one possible tree. There are many possible trees that you could come up with an equivalent encoding. Let's go ahead and look at one that's a little bit cleaner. There's the tree. That might actually be the exact, nope, it's not the exact same tree, but it's pretty darn close. Right? It ends up with all the same values at least. Right? Now, how do we do our encoding? The way that we do our encoding is by associating a left child with 0 and a right child with 1. Again, you can flip those around. A right child with 0, a left child with 1, and a right child with 0. Depends. Entirely what you want to do. It will lead to an equivalent Huffman code. How do we know what a code word is? Here's our character. What's our code word? We start at the root here. And then we traverse down until we get to that particular element. All right? So if I go left, and then right, A is associated with 0, 0, 1. 0, 0, 1. Okay? What about B? C, D, E, F. What about, where is B? Right here? Another way that you can do this is you don't have to start at the root. If you can go ahead and start at the leaf if you have access to it, and do what? Go to the parent, go to the parent, go to the parent, and then make sure that you reverse it. All right? Why reverse it? Because generally you would go down. It doesn't matter. Again, you have an equivalent Huffman code if you reverse everything as well. 1 0 1. 1 0 1. All right. C is right here, and it has a code word of 1 1. Where's D? All right. 0 0 0 1. E is 1 0 0. F. I had G, right? Yeah, all the way to G, sorry. F is where? 0 1. And G is 4 zeros, right? There's a Huffman code. Okay. Put that off to the side here. Now let's make some observations. Remember, we had some goals. First of all, we wanted to make sure we're sunk if this is not a prefix-free code. All right? We need to make sure that it is prefix-free. Is it prefix-free? Verify, at least for this one example. Is that a prefix of any of these other code words here? Nope. Is 1 1 a prefix for any of these code words over here? Nope. So I'm convinced that it's prefix-free, but that doesn't suffice as a proof. What would suffice as a proof here? Why is it prefix-free? So observe what forms a code word. We go from a leaf up to the root. Or equivalently, you can go from the root down to any leaf node. In other words, a code word corresponds to a path in this tree. How many paths are there between any two nodes in a tree? 1, right? There is a unique path here, right? And so what if there were something that was a prefix of another one, right? In other words, we have, 0 0 1 1 0 whatever, and then there's our code word, right? Say our code word is right there associated with that, and then we go on to this other thing right here, and so it ends up being 0 0 1 1 0, and then more stuff, 0 1 0. Right? Is that possible here? Sorry, what?
And there would be a node, this blank node wouldn't be
Exactly. This one right here, would that end up being a leaf? Nope. The idea here is that we started out with all the code words being leaves. Combine that with the fact that there is exactly one unique path from the root down to any leaf, and you have a proof that all these characters will be prefix-free. Right? By way of contradiction, suppose that you have this, right? That implies that there is a code word associated with an internal node which violates how you began with the algorithm. Right? That's the outline of the proof. Okay? So, task 1 done. We have a prefix-free code. Did we achieve optimality, though? Remember, what we wanted to do was we wanted to associate common letters, like RSTLE, with shorter code words, and less common ones, things with smaller frequency, with longer keywords, or longer code words. Did we achieve that here? What was the original frequencies? Frequencies of A? 0.1, 0.15, 0.1, 0.15. They're all over here too, right? So what was B? C. Oh, I guess I already did B. 34. D is 0.05. G is 0.03. F is 0.21, and E is where? 0.12. There we go. So did we sort of do that? Well, what are the least frequent ones are D and G, right? And they have definitely the longest code words, 4 and 4 respectively. Why? We iteratively combine the two least weighted ones first, ensuring that the two least weighted ones are going to be the deepest in the tree. Being deeper in the tree is associated with a longer length path, in other words, a longer code word. Right? Shorter ones, like I don't know what's the most common, C here, they were shallower in the tree, right here. C and F are the shallowest in the tree, right? And because they have the highest frequency, we wait until the end to combine them into the tree. By going least weighted first, we're ensuring this kind of greedy approach where shorter code words here are going to be associated with more frequent characters, commoner characters. Right? We can actually measure the compression ratio on this. So if we, what's the expected code word length? That's different from the actual code word length here. The code word length is going to be 3 bits to encode an A. But an A appears 10% of the time. So in expectation, if I were to randomly pull out a code word, what's its average code word length? What is the average code word length? To compute that, all I have to do is multiply the actual code word length, 3 here, by its frequency, and then sum them all up. So 0.1 times 3 associated with this, 0.15 times 3 associated with that, 0.34 times 2, 0.05 times 4, right? 0.12 times 3, 0.21 times 2, and then finally the last one is 0.03 times 4. If I sum those all up, pull out your calculators and do it, otherwise I'll just tell you, right? It's 2.56, I think. Don't quote me on that until I've looked it up. Let's see. Sorry. 2.53. There you go. I missed it. That's the average code word length. So is that better than just say fixed length encoding? If we did ASCII, then it would be 8 because that's just fixed. 8 or 7, depending on how you want to look at it. But we don't have to stick with ASCII. Right? What if we considered a fixed length encoding? How many bits are required to encode A through G? Remember, there are 7 characters. What's the minimum number of bits that you need to encode 7 characters? Can you do it with 2 bits? 2 bits is going to be 0, 0, 0, 1, 1, 0, 1, 1. That's 4 things that you can encode. 3 bits? Why? How many things can you encode now? 8, right? So you need 3 bits. Right? I hope we all know that, right? We just didn't want to say it. All right, good. Because over the weekend, I was a reviewer for the AP CS test, Advanced Placement Test for Computer Science, and well, it's not violating the exam to say that there were at least 3 questions asking about bit length stuff, and I had no idea that they cover that in high school. Do they? Like binary stuff? Okay, great. Like, I was really pleasantly surprised that they would cover that in high school AP stuff.
Principles or
Principle, even principles covered it. So I was like, wow, okay. Over the weekend, my respect for the AP principles test increased like 50-fold because I took the exam and I reviewed it and and sent in my review. I didn't do it for free. There was an honorarium, but I was pleasantly surprised at the content of that exam. It's the easier one between the two, but it's not at all a cakewalk. I would definitely say that it would certainly count for 101 here. The problem with that is the principles class does not require like a full programming language. Like you could offer a principles class with just Scratch and no Python whatsoever or something. And that probably wouldn't cut it. But if you pass that exam with a 4 or 5, you certainly get credit for 101, and you are well prepared for 155. But in any case, they asked almost virtually this question right here. They gave like a range of stuff and asked how many what's the minimum number of bits that are required to encode this. Not this exact number, but that same idea. So did we achieve any compression? Yeah, because we achieved better than the 3-bit characters, right? That if everything was just 3 bits, 3 bits, 3 bits, 3 bits, then however many characters are in the file times 3 bits would be the size of the file. But instead, we've got 5.53 or 2.53 bits, which gives us a savings. 3 minus 2.53, all divided by the original, right, is going to be a 15% or 15.67% compression ratio. Compression rate. Right? That means that if it were 1 megabyte before, now it's only going to be about 850K. Right? We cut it down by 15%. That was just a toy example, right? In real, like actual natural language, you can achieve up to 60, 70s, 80% compression rate with Huffman coding. Okay. All right. So, in the last 10 minutes here, we'll come back on Wednesday and look at the actual code because I do want to go over the analysis of this. But let me go ahead and get you started. Yeah, while we're restarting here, go ahead.
Is it because more letters are involved so that the compression rate is higher?
No, it's not because more letters are involved. It's because there's more structure, right? It all has to do with entropy and entropy rates. Like there's low entropy, I never get them correct. I think there's low entropy, high information content with actual language, right? If I just mash the keyboard at random, there's no information there at all. That's just random data, right? It would be high entropy. But if it's highly structured, actual English words, right? Then that's high information, low entropy, I think, right? Anybody? I always get those confused, just like sine, cosine. But in any case, what I wanted to do with our last 10, 15 minutes here, whatever we've got, is to get you started because this Huffman Coding is your other programming exercise for this Friday. I'm not going to go through the entire thing, but I will help you out on getting started by computing the frequency. So, given a file or string, right? What you can do is you can read the entire file in, treat it as one big giant string, right? How do you easily, right, compute the character counts frequencies, right? So for that, let me go ahead and give myself something to work with here. A classic string, right? You might have seen it before. It's lorem ipsum text, right? It's Latin, it's Latin gibberish, right? And it's used as placeholder text, right? So I want to count the number of I's in there. I want to count the number of A's. I want to count the number of whatever. You can do that by saying s.count however many I's there are in there. And print count. How many lowercase i's do you think are in there? Lots because it's Latin, right? The number of I's I have has no bearing on whether it's Latin or not. It's a vowel, and so it's going to be very common. Python demo, there we go. There are 42 I's. How many capital L's are there? I see one. Right? That's the only one. How many Q's? Oh, there are some. What about Z's? Are there any Z's? Okay, 0. All right. So 0 Z's. Remember that. We've got one capital L. We've got many lowercase i's. We've got 0 Z's. Okay. So if you've got a string here, you can actually count the number of subs. This is actually a substring here, but I'm treating it as one character because that's what I want to do. All right. That's one piece of the puzzle. What I want a map, a dictionary, such that each character, each unique character, maps to its count. So for example, what I wanted was L maps to 1, right? I maps to, what was it? 42? 42, there we go. And then, of course, Z would not be in the map, dot, 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 because it doesn't even appear in the string. Ideas? Oh, okay, yeah, yeah. I'm only doing this demonstration so that we can get away from loops, actually. Right? I want to show you comprehensions. So list comprehensions and dictionary comprehensions. If you write a plain old loop, that's fine, right? But that's not the Pythonic way, right? So first of all, what I want is, let's get a list of unique characters, dot, dot, dot. So lists are not unique, are they? What are unique? Sets. So a set of S. What will that do? Foo is equal to set of S, print foo. It will give me, split up, all of the unique characters. You can look through that, but I does not appear more than once. Why? Because it's a set. What I'm going to then do is translate that into a list by surrounding it like that. Yeah, go ahead.
Is the set ordered?
Sets are not ordered. Nope. So these are my unique chars. Right. There we go. And it's also ordered. It doesn't have to be ordered. It doesn't matter. But I'm showing it to you that you can order things. Okay? So here's a basic list comprehension. Right? Basic list comprehension. Right? So if you remember, say from 235, you can do a set builder notation. Something like this. All x such that x in z and x is even. You can write mathematics like that. And in Python, you can do something very similar, right? I can say foo is equal to x for x in S if ord of x is greater than 100. Right, there we go. It looks kind of like this, in that there is a set builder notation like this, but I'm using actually a for loop within this. For x in S, let's read that part first. Come on, nope. Exit, Control D, sorry. All right. CSE 310. Okay. So let's read this list comprehension to see what it does. First of all, x is like that thing in the set builder notation, all the x's, such that for x being in S, if the order, in other words, the ASCII text value of x is strictly greater than 100. So what am I kind of doing here? ASCII values 65 through 91 are going to be excluded. What are those? Uppercase letters, right? So let's go ahead and print this out. Print foo. What do I get out of this? There we go. All lowercase letters. Right? That's a basic list comprehension. That won't be too useful for what we're trying to do. But what can you do now? You can do something like this. Bar is equal to join all of those things together from foo, and then print that out. Print bar. So it's taking all of those letters and then recombining them into one big giant string. And you'll note here, what have I done? I've stripped out all white space. I've stripped out all uppercase letters. I've stripped out all ASCII text values 100 or less. Okay, that's kind of fun. How do we use that idea now? Okay. Here's a dictionary comprehension. The syntax is very, very similar. What I'll do is say, use the exact same syntax here, but instead of square brackets, curly brackets. Curly brackets gives you a dictionary. All x such that x times x for x in, and then I don't have a value here, so let's go ahead and go array is equal to 1, 2, 3, 4, 5, right? In array. There we go. Now, sorry, this is not such that. This is mapping, right? With a dictionary, you have the key, colon, and then the value that you're mapping to in Python, right? So what is this doing? It's going to map x to x squared for x being in this list up here. Now let's print foo. What's going to be in foo? It's going to be a dictionary. What are my keys going to be? 1, 2, 3, 4, 5. And what are my values going to be? 1, 4, 9, 16, 25. Yep. This is the key. This is the value. So now that we understand that syntax and how it's powerful, let's do what we were going to do. I want a dictionary such that each unique character, which we have, maps to its count, which we know how to do. All right? So bringing all this stuff together here, char counts is equal to all characters such that, which will map to s.count of the character for all the characters in, what was that unique character? There we go. In that original up there. So all you have to do is read that in English. All characters will map to the count of the character in the string s, which is our lorem ipsum text up here, for each character in the unique characters list. Right? And then let's print out char counts. Oops. Counts. There we go. Huh. There we go. Now remember, Z did not appear. I, which appeared 42 times. And capital L appeared once. What else do you see here? I see punctuation. How many times did the comma appear? It appeared 4 times. How many times did it looks like it might have stripped white space. I don't know, did it? You certainly don't want to do that. Where's my 68? Where is that? Oh, there we go. That's the space. Oh, and then there were no end-line characters because it was just one single string. Right? But it preserved all those things. But don't cut those out. You will encode those in your assignment. But there. 1, 2 lines of code. In fact, you could do it all in 1 line of code. Instead of saving that off into a temporary variable, you can do this all in 1 line of code to get all the character counts. Right. There we go. And we're done. Right. Now, eventually you're going to want to print them out in order. Can you sort counts? Can you, well, not by value, but can you sort it in lexicographic order? Can you sort a dictionary in Python? That's a good question. Can you? Can you sort a set in Python? No, because a set is unordered. Right. Sorted, or not sorted, is it? There we go. Is it going to do anything? Apparently it's not an error. I would have expected it to be an error telling me that you can't do that. But apparently you can, but does it do anything? Oh, maybe it does. Oh, no, it does not. Right? L, A, X, G, V. That's definitely, that's no discernible order that I can tell. Right? So can you just sort you can sort the keys. You can do something like this for key in sorted character char counts dot keys. Right? Take out all the keys, sort them in lexicographic order, and iterate over them in that order. Right? Print. Let's go with a formatted string here. The key maps to, the value, which would be char counts of key end. There we go. Same exact thing, but guess what? Now it's sorted. There. DELU, well, why? Because in the ASCII text values, uppercase come in before lowercase. Then we've got lowercase here, A, B, C, D, all the way to X. Remember, there were no Z's. Right? So there's some code to get you started. It's a one-liner, and that's it. All right, very, very powerful list comprehensions, dictionary comprehensions. Now I'll take off my Python nerd hat for a second and say, it all works great when you're doing stuff that it was designed to do. The second that you're trying to do something that it was not designed to do, you're bending over backwards fighting the list comprehension syntax to get what you want. At which point, screw it, write a loop. Right? So it's not a cure-all. I mean, it seems amazing. It's amazing that you can apply it to very, very simple stuff like this, right, and gets the job done. The second that you have anything complex or non-standard, or you're trying to solve a problem that doesn't fit into this kind of world, it all blows up. So it's not a cure, right, for all problems. All right, we'll pick it up there on Wednesday with some more analysis.